Welcome to YMT215 Logic Circuits. We are still discussing the topics of chapter 1. This is the third and last part of this chapter. We speak about the introductory concepts, and we have another 3 topics. We need to discuss introduction to programmable logic, fixed function logic devices, test and measurement instruments. So previously we spoke about the concepts of logic itself and digits. So we consider the digits or digital systems, we compare them to analog, and also we spoke about the gates and how we represent certain devices or certain functionalities, logic functionalities using these gates. We didn't design anything yet, we are not supposed, we will later on, but now once we have an idea, once we have had an idea about those, so what are we going to do with them and how we compare them to realistic things that we have in hand. That's why we are studying the programmable logic, a logic that we can program on our own, and a fixed logic, a logic that we can use, we can't program, it comes actually readily programmed, we can just use it, and how we test and measure in logic, either programmable or fixed logic devices with certain instruments and measurement devices. Right. First of all, we have actually 2 types of hardware based on the software programs them. We have what we call programmable logic devices, or PLDs. These are programmable. That means we or experts can program them, okay? And based on that, they are more flexible, okay? So, well, when we say they are programmable, either experts or we programmers can program them and change their functionality. So they are more flexible. They may actually have less space than fixed function logic. Why? Because we may have the smallest possible that fits our own need, while fixed function logic come with a standard form. So if you buy a chip, usually they come in a chip and we will see them, you can change it, you can shrink it, you can change its size, you can change also its functionality, you have to use it the way it is. But for the PLD or the programmable logic device, you can buy the minimum that fits your own need, okay? For the fixed function logic, the fixed logic IC or device in this case, you need to wire it. So once you wire it, if you need to use it for another device, or if it's necessary for using it in different wiring in another circuit, you need to rewire it. But for the programmable logic, no, you need to just reprogram it. That's another way. So simply, for programmable logic, it's more adaptable, it's more flexible for different implementation and use for digital circuits, while fixed function logic is actually supposed to be inserted to the board circuit or the circuit board and kept there for long term. So if you are designing one-time machine or one-time application or one-time device, you can use fixed function logic if it is cheaper, if it fits your own need. If you're going for some reprogrammable or something that you may program in future, you may think about PLDs or the complex version of PLDs. Okay, so let's first discuss programmable logic, then we will go to fixed function logic. For the programmable logic, we have 2 main types, PLDs and FPGAs. FPGAs are field programmable gate array. They are based on field programming along with array of gates, and we will see them, how they are composed. For the design, not now. I said this chapter is about introduction. We don't have any design, and we don't need to discuss the details of the components or the details of the circuits. All right. So for PLDs, we have actually the simple type, simple SPLDs, simple programmable logic devices, and we have the complex programmable logic devices. So we have these two, and we will explain why it is referred to by simple and complex. All right. So I said earlier, the idea of the programmable logic device is actually having flexibility in installing or programming the device itself, or installing a program on the device itself. So we change its functionality based on the code that we install in it, or the program that we set on it to do certain functionality. Okay, so in that case, the initial version of PLDs was the simple one. The simple one actually is a small scale, has a small scale application. It's not that much large. It has like up to 10 fixed function ICs. We will speak about the fixed function ICs soon, but instead of rewiring and replanning the whole circuit, that electronic circuit or the board circuitry, we can just reprogram a simple PLD to do a job of around 10 or up to 10 fixed function IC. In that case, that was the first or the initial version of PLDs, and we have actually two types of them. The simple programmable logic control device, logic devices. We have two types. The first one is called programmable array logic. We have an array of gates, but how it is designed. Gates, we refer to gates here, and an OR. We don't use NOT frequently in this design. However, we have an array of AND, an array of OR. Now look at this. Programmable array logic, PAL, consists of actually a programmable array of AND. So let me show you here. This is programmable array of AND. We can program it. That means we can rewire its connection by a program. Maybe this program would burn a fuse or something. We will study it later on. And another array of OR, which is fixed. Then this array of OR shows us the output. Okay? So the programmable part is an array. Array, you know that we have rows and columns. So we have rows here and columns. So it's like a square or rectangle of gates interconnected, and we have inputs. We can program those based on connections, the inputs, okay? And their outputs are actually joined by an array of OR, and this OR is not programmed actually, it's fixed. We take all the connections, they are set from the beginning, we don't change them. And the output will be based on the programming here. So what we program here, what we wire here, or what we keep as connections for the AND gate, you know AND gate, the output of AND gate is based on its inputs. So whatever you input in that case matters. So that's exactly how we program it. We will study this later on in details. Okay, so the first one, PAL, consists of a programmable AND gate. And this AND gate, programmable AND gates, array of programmable AND gates attached, or they feed their output to a fixed array of OR gates. Okay, and then we have the output here. All right. The second type of the SPLDs is the generic array logic. Generic array logic, GAL. This one, GAL, actually consists of programmable AND array, okay, array of AND gates, okay, and also fixed OR array with programmable output. We have fixed OR array gates, but we have a programmable output. So we can program the connections here for AND, and we can program the outputs here for OR. And that's the main difference. Okay, we will take those in real design later on. We have them. Now, what do you need to know? You need to know the difference, the main difference. For PAL, the array of AND is programmable, and it is used for the input, and we have fixed OR, which has no programmable output. Okay, it's just used to provide the output from its side, and there is no programming for the output here. For the generic array logic, GAL, it has a programmable AND array, so we have a programmable here and here as well, but for the output we have the fixed OR array. It's fixed, but the programmable side is the output. This one can be programmed, and we will see how. All right, for the complex, actually the complex PLD, or the complex programmable logic device, is composed of combination of those. Either the generic array logic or the programmable array logic. So it's just a combination of them. We interconnect them to accommodate actually more complicated applications or more complicated needs. So instead of accommodating up to 10 fixed function ICs, maybe we need 100 or 200. So we need certain combinations of GALs or PALs to accommodate that. Okay. As I said, in the first scenario for both PAL and GAL, we expect to implement limited fixed function ICs or certain logic applications, and for that we do not expect variety of applications or more complex applications, but for complex PLDs we can accommodate actually higher level logic functions. What does it mean? Higher level logic functions include decoders, encoders, multiplexers, maybe even memory. Okay, so it is for higher complicated applications. The types that they come for CPLDs, there are actually different types. The most common one range from 44 pins to 160. What are these pins? Now let me explain on the package here. Look at those. These are like legs, you can say. We call them in technology or scientific term pin. So this is a pin, and this is what we call packaging. The outside here you see is not the chip itself. It is actually packaging. Usually it's some sort of plastic, composite of a plastic that covers the inside, the inner chip here. Okay, it ranges from 44, so maybe this one is around 44 pins to 160 pins. The more complicated, this is 80 actually, not 44. 128, this one. There are ranging from 44 to 160 pins, depending on the packaging type and the application we have. Okay. The second type that we explained about earlier, the field programmable gate array, the FPGA. This is also one of the up-to-date actually programmable logic devices that we have. Usually it is more complicated than the PLDs and also the complex PLDs. So they accommodate higher functionalities. So we have a logic design, and these logic designs or logic circuits that we need to create are designed or are built based on either PLDs or complex PLDs and FPGA, depending on how complex and how the density of the circuits is required or actually is needed. So basically, if both CPLD and SPLD do not fit, are not enough for composing or creating the electronic or the digital circuit, in that case we may think about the FPGA. Okay, so FPGA itself is composed of three main parts: the logic block and the programmable interconnections, and finally the input and output. Now look at this. We have the logic block somewhere in the center. It's like an array. It depends on the application how many. So this is the field actually, programmable field. Okay, and then we have the outer input and output, and then we have programmable interconnections. Okay, so we program it by these interconnections. Now, how do we do that? Not now. We will have it when it's time. You just need to understand it as a type. Now we have two main types for the FPGAs. We have the first one when we have actually simple architecture. So these blocks, when we have these blocks, are actually relatively close and simple. We call them fine-grained. Okay, fine-grained, that means they are too close to each other and their composition is simple. Okay, if they are large, these blocks are large and they are a bit far from each other, then we call them, in that case, coarse-grained. Okay. The programming process, we spoke about programmable logic device or field programmable, okay, array. So both PLDs and FPGAs, PLDs, that means both of them either simple or complex, and the FPGA, all their types, come usually with a blank state. Blank state means what? They are empty. They don't have any programming functionality in them. So they need to be programmed. For us, programmers or those who deal with electronic devices or digital circuits, we need to program them based on our own need. So when you buy a device, a programmable device, you buy it for a need that you need to program it. How do we program it? We need to have an interface between our computer and this device in order for us to create a program for it and download it to it. But it's not that much simple, okay? We have a certain need to do this kind of process. Now look, this is one type of designing programs. Actually, I personally would prefer to use something that we will use for practical. Let me show you. This is what we call multi-sim. Multi-sim, I'm using this the 14th version of it. You can try to find it and get its license. I think we have the licensed one. You can contact our lab technician and ask about the licensed version of this device. Sorry, of this software, because it is payable. Actually, it's not free. So try to get the licensed one from our university. I think you can get it. Okay. This software allows you to design, to create digital circuits, or actually analog can also be, but logic circuits, because we are teaching logic or digital circuits. So you can create the circuit first, then you can convert it to whatever bit stream or simulate it, and then you can have that certain functionality of tool that allows you to connect the device you need to program to a circuit, like a programming board circuit. Okay, so we create it in software, we simulate it, then we need to install it to the programmable logic device. Initially, how do we create our own design? There are different software packages. The software that I showed you, multi-sim, allows you to design in graphical user interface. You can also use HDL or VHDL, maybe Verilog also if you want. That is writing codes instead of using the high-level design, which is graphical user interface. You just add and drop components, drag and drop components and connect them. Either text-based or graphic entry. So I was explaining about the graphic entry. So you drag and drop components and then you link them, you connect them together. Let me just show you quickly. Let's say I want to create a very simple connection. I can place a component and this component here. What I'm going to do, I will choose the component that I'm adding. Let me put AND gate. So look, this is AND. You want AND 2, 3, etc. Let me choose 2. So add and drop. You can put its specifications if you want to change its specifications. If you are happy with it this way, with its name, that's your component. That's it. And there are other ways to write it in codes. So instead of using this drag and drop or just assign a gate that comes to you graphically to the machine here, to the software, you need to write it in a code. And I'll teach you about VHDL or HDL, like a little bit. I give you an idea about it. I don't want to go in deep in programming it because it's a bit actually hard for your case in this course. We will just use the graphical way, add and drop or drag and drop, okay? So this is an AND gate, you can specify it, or if you are not using, this is the ideal one. And I explained the difference between ideal and the practical one. We can use the family, exactly the family of the gate, AND gate, which family is created from, because ultimately it's actually a semiconductor. It's composed from some transistors, and based on that they have their own data sheet, they have their own specifications or characteristics, and we need to know these characteristics in order for us to determine if there is a delay, time delay between the input signal and the output signal and so on. And now maybe it sounds to you a bit weird. Don't worry, I'll explain about those within these slides. Okay, so the design entry, I showed you how we can just, let's say, drag and drop or drag and add AND gate in one of the software packages, the multi-sim. There are other software packages. You may just use text-based, like, for example, you are familiar with maybe Java or C or C++. Now, in order for you to write a code, you can write with certain instructions. Also, for logic circuits, we can have certain instructions to add an AND gate or an OR gate or not, or to have certain assertion. In that case, we can use those instructions to create the circuit instead of the schematic diagram. Usually we go for graphic entry, it saves time and effort. Also, there is a state diagram description. We are not going to study this. I say from now. We are not going to study it for the design. We will just go for graphical entry. I will give you a little bit of an idea about the text-based. Maybe some of you will need to use it in future. Okay. Once we are done with our design, so what we will need to do, we have created our design that we need to program our PLD or FPGA based on it. We need to run it and see. So we need to compile the process that we created, and then we need to check if it is working or not. So this is what we call functional simulation. Functional simulation, you simulate whatever you created before you download it to your own device. Why? Because if you download it with any mistake or flaw, it wouldn't work. And for that reason, we need to have functional simulation. Right after the functional simulation, if we confirm that our design is working in a good way, there is no problem, there is no any design issues. If there is any, we can fix them. Once it is done, it's properly simulated, then what we can do is we synthesize it. Synthesizing is actually translating whatever compiled simulation that we created into a netlist. Netlist that is actually a standard fits our own device. Why? Because for PLDs we may have some standard, for FPGAs we may have some standard, but the process of simulation, your functional simulation, is a device independent. It's not dependent on the device. It's dependent on the software package that we are using or the text base of the programming and so on. Okay? Once we synthesize it, we need to implement it. Implement it, that means transferring its case or state now to something that fits exactly the device we have. So it's like mapping or fitting. Once we mapped it to our device, what we need to do is a timing simulation. This is the last part of testing. Why timing? Because we may have a problem with the propagation delay. We think about like our devices, our gates, our components, maybe ideal or maybe with no delay, but when we try to practically test them, we find some delay, so that we need to make timing simulation and see if there is any delay or not. If there is no delay, then that means our software is ready to be downloaded to the hardware or the tool that the device that we have. And in order for us to download it, it has to be in the form of a bit stream. A stream of 1 and 0. And that's exactly a program. So in order for us to download it, there must be the proper software and hardware tools. Software, now look at this. Software could be a multi-sim or any other package that we use, but we need to have a circuit board for programming. Okay? and some connector between your PC and this circuit board. So you can program some of the PLDs, FPGAs, and whatever. Okay. This is the process. Do I ask about these things in the exam? I don't ask you to write or list down all the steps, but I may ask you, why do we need to have implementation or an implementation step in during the programming of a PLD or an FPGA, for example? Or why do we have a timing simulation while programming a PLD? So you need to know this. So as I explained, maybe there is a propagation delay, so we need to count for that if there is any flaw in the timing. Okay. I may ask a question like this. What kind of design entry do we have while programming, let's say, a PLD or an FPGA? So you say text-based, graphic entry, or state diagram. Okay. So now you understand the type of questions I may ask. All right. So I spoke about the programming process of those. We have just one final piece. This is a very specific, actually, topic about how we can exactly program the device. Do we need to fit it on a development board for programming, or we need to use something we call in-system programming ISP, or something we call the standard JTAG, the JTAG Joint Test Action Group. So these are a bit high or advanced topics. You don't need to go to them, but there are ways to program based on the device itself. In order for you to install what you create as a design, you need to know your PLD or FPGA or the programmable logic device you are using, what fits it. You need to use ISP, JTAG, or you need to use some what we call development board or anything relevant to that. It depends. It depends on the component that you are programming, the device that you are programming. Sometimes we said that we have a program. Once we create this, like this is my design. Look at this small part. This is my design. I compile it. I transfer it to a bitstream. I create my own program. I want to download it now. Now maybe the PLD itself has a volatile memory. That means once you turn off the electricity, whatever on the PLD or whatever on the programmable logic device goes off. It's erased. So when you turn off the electricity or you unplug the electricity, it's erased. Why? Because it has a volatile memory. Volatile memory means like a memory that doesn't hold its components when the electricity goes off. Okay, and in that case, you need to reprogram it again and again and again. Is that practical? No. In that case, you need to attach a ROM to it. ROM, read-only memory, a memory that holds this design and keeps it. When the electricity kicks in, it loads the program back again to the PLD. It's very similar to the BIOS of our system. They are stored on a ROM and they are loaded each time we start our PC or machine. Okay, and this is the idea. So if I ask you this question, why do we need to have why is it necessary in certain cases to use an external or an attached ROM to a PLD? You say simply because some of them have a volatile memory design, so they lose whatever content they have when the power goes off, and once they lose that programming functionality or the program that they have in them, they become useless. And in order for us to reprogram them, we don't need to do that every time. Instead of that, we have an attached ROM or an attached memory that loads this program when the power goes on. Okay. So this is the schematic diagram of programming process. We have the development software. We can say multisim in this case. There are others also. Design entry, it could be graphical, it could be HDL, VHDL, or Verilog, or any of the programming languages used for logic design. Functional simulation, remember, synthesize, implementation, timing simulation, and then we download it to the programmable device. Now, we have actually two common types of these programmable devices. We have the microcontroller. Microcontroller actually is a special purpose computer, and usually it is small in size, designed for certain purpose. So when we say certain purpose, that is an embedded system. An embedded system actually is a computational ability. It's a tiny computer, a small computer, or a small programmable device. We needed to do certain things, one or more actually functionality within a larger system. So that's what we call embedded system. Okay. Usually it's designed with a computational ability that allows us to do specific functionalities, usually very limited, not versatile. Like our computer is versatile, you can make so many tasks with it, but the embedded systems usually not. So we call them microcontrollers or small computers, if you like, specific type computers. Okay. Now, I said earlier we will speak about fixed function logic and its time, and now exactly this is its time. We refer to them usually by integrated circuits or ICs. So an IC is actually an electronic circuit. It's designed as a chip, okay? And this chip is made of semiconductors. You know semiconductors, you studied them in chemistry, maybe in high school, or physics at the beginning of university, I'm not sure. Usually silicon or germanium, it depends on the type of the material or the composition. It could be made of a transistor or multiple transistors in a circuit. Now we are not going to that side, sorry. But the idea is any IC is made of compositions of transistors. There could be also diodes, also resistors, maybe in some specific cases capacitors, but we will not have something like inductor. Capacitors can be composed also from semiconductors, but inductors are not permitted in such devices for only one main reason. They are bulky and they create actually an electromagnetic field, and that's not recommended when we design chips. So basically, combination of transistors, diodes, resistors, and capacitors all together on one chip. What's this chip? I will show you in photos in just a few minutes later. Okay. What's the difference between a PLD and an integrated circuit, or actually a fixed function logic device? They are actually same as they are designed, except for only one thing. One of them come programmed from the manufacturer. We cannot change it. So the manufacturer gives it to us programmed, so you can use it. So you buy it for its specific programming functionality. But for the PLDs or the programmable logic devices, you buy them, you program them, or you take them to an expert to program them for you. Okay, look at the chip. This is the chip we speak about. Usually for the fixed function, they are a bit bulky, a bit bigger than the programmable one. And they have these pins again. These are connecting legs, we call them pins. And this is the plastic case, the packaging case. And this is the chip. The chip is extremely small actually. So do not be puzzled if you see this one. I'm sure you have already seen this one in reality. But the packaging takes most of the space, more than 90% of the space, plus the pins, the connectivity of the pins. Why? The chip can be extremely small, but how can we connect these two small chips to their own connectors? So the manufacturer connects them to their own connectors, pins, and we just need to connect these connectors. And one more thing, these are versatile. We can use them for what we call breadboard. The breadboard is, we can insert this chip directly to connectors. I wish we could go to labs to show you how we can connect this chip directly without any wiring. We just place it to its own connectors, then we can wire if needed for other let's say applications, but this one will be just fitting inside a ready designed connectors on the breadboard. Okay. We have two different types of packaging. The first one, we call it through-hole mounted. For the through-hole mounted, usually we have longer pins, and they pass through a hole on the circuit board or the printed circuit board, PCB. This one is used for the design. We have standard PCBs. You can buy them and design your own device based on whatever the fixed function or programmable function logic or whatever you want to add to them. But in this case, let's say we think about this mounted, the through-hole mounted. We need to pass this pin inside the hole and cut it from other side, and then use some soldering functionality to attach it properly to the board. Okay, we have one common type, we call it inline package. It's called DIP inline package, dual inline package. Okay, like this is dual inline package, actually, DIP. And we have also the surface mounted. The difference now is this one is tiny. It doesn't need its pin to go through a hole and then cut, and we apply some soldering from other side. Now, no, soldering is applied from the same side, from the same surface. That's why we call it surface mounted technology. It saves space, and it's simpler, a lot simpler than the other one. And in that case, suit your own application. If this one fits you, you go for this. If this one is more suitable for your application, you can go for this. I said earlier, we have some certain design goes with the breadboard. With the breadboard, this one goes with it. Why? Because we may need to plug it and unplug it. We don't need to put it for, like long-term application. We may need to change its place or change its connectivity. But this one doesn't fit. Its pins are short, so they fit the printed board, actually, circuitry board. And in that case, this one fits like long-term applications more than this, although both of them are used. However, this one doesn't fit the breadboard. The breadboard is actually reusable electric board, usually used for educational process, not for a long-term design, and it is actually bulky. For the printed actually circuit board, it is extremely tiny and thin, and it fits the electronic design for long-term. Okay. So now there are different types of this. The surface-mounted technology, SMT. There are so many. Well, one of the common types, we call it small outline integrated circuit, SOIC. This is one of the common types. There are other common types. I don't ask those on the exam, but they will come along with us while designing some of the devices later on. There are so many of them. I don't ask those on the exam, just for you to know. And actually in your course, you are not required to know all of them. Just one example of them is enough, like this. Small outline integrated circuit, or SOIC, is one of the common types. Okay, these are all types. Not all of them. They are types of surface mounted. So they are all common types you may see for the fixed function logic devices. Now, one more thing. Pin numbering. We spoke about pin. These are pins. This is a pin, this is a pin. So from where we start, how about the numbering? Which one is 1, which one is 2, and so on. Now look, this is like an indication, identifier for the for the pin. So if you don't have this identifier, you need to know there could be another way to know. Either it is written, or they provide you with a notch. Now look at this. This is what we call notch. So if there is a notch, you go to the left direction, you count. Number 1, then counterclockwise, so opposite to the direction of the clock, you count 1, 2, 3, 4, 5, 6, 7, 8, and go on. If there is no notch, there is an identifier for the pin number 1. This is like here we don't have any notch anywhere, so we have an identifier. So this is 1. So where is 2? We said counterclockwise, opposite to the direction of the clock, 2, 3, and so on. Okay. The complexity of the ICs. Now we spoke about the fixed function ICs, those who are readily designed and programmed. We do not reprogram them. They are already programmed. They come with ready programs on them. We have different types. The first one, we call it small scale integration, or SSI, usually up to 10 equivalent gate circuits, 10 AND or not, or combination of them. Okay, so 10 up to 10, usually they compose flip-flops, the smallest memory. Okay, then we have medium scale integration, the MSI actually between 10 and 100, that's a bit bigger, and they form on one chip like this. Okay, we said gate circuits, or circuits composed of gates. And in that case, we have bigger functionalities like maybe decoders, encoders, counters, registers, multiplexers, maybe adders, subtractors, and so on. Okay, small memories also possible. Why? Because if you compose, let's say 10 flip-flops, then you have, or 8 or 10 flip-flops, you have like ability to store 10 bits. And that's a small memory, 10 bits, small memory, or 1 byte, 8 bits, that's a small memory, okay? We have large scale integration, LSI, between 100 and 1000, and that's usually for average size memory. Average size memory takes you between 64 bits to maybe 1 kilobyte or so, okay? That's a small memory, sorry, not small, average memory. Okay, we have the very large scale integration. VLSI is actually the beginning of the current revolution we live in our computation industry. VLSI, these are ICs that have more than 1,000 and up to 10,000 equivalent gate circuits on one chip. They compose small microprocessors, average memory size to large memory size, and so on. And then the final one, the one we have in our today's modern era, we have the ultra large integration ULSI. They compose more than 100,000 equivalent gates on one chip. That's really too much. And that's how we compose memories like the SSD memories, the flash memory, and so on, large microprocessors and large single chip computers. Okay, these are used for the versatile computations ability we have today in today's era. Okay, the last part, we have the test and measurement instruments. Why are we teaching those? You need to know the devices that we need to deal with, even in simulation, because they are available also in simulation. You need to have an idea about them. The first one is the oscilloscope. The oscilloscope is actually a device that plots waves for you. And it also allows you to see these waves on the screen like this. You see, these are waves. And you can modify the view the way you like, vertically, horizontally, or whatever. Then also you can measure the amplitude, how big this amplitude is in voltage, for example. You can think about the period. It calculates for you the period. It calculates for you the frequency, the pulse width, the duty cycle, the rise and fall time. You get all those. Now you say, maybe, what will I do with those? In the proper time, we will speak about these applications and why we need them. This is a front view of an oscilloscope. We have also, usually the common oscilloscope has 4 channels, okay, 4 input channels. So you can input up to 4 signals from sources, output sources, and they will be displayed here. And you can use vertical control or horizontal control. You can move those to this direction or up and down, and you can use the rest of the functionalities based on what the application dictates or needs. There is also printing, by the way, or save. You can save these signals to a digital output. Okay. Logic analyzer is it's a bit bigger than the oscilloscope and has more functionality than it. What does it mean? This is the oscilloscope. Now look at it. I'll come back to the slide and explain. It actually analyzes a higher number of signals with much more functionality than the oscilloscope. Now we spoke about the oscilloscope. You can get the amplitude, the period, the frequency, the duty cycle, and the pulse width, and so on. Well, this one will get you so many signals, not 4 only, 4 inputs. Plus we have different types of analysis. So for that reason, there are actually more channels. So we have so many inputs here. Look, 16 to 136 channels. That's really much. Plus the composition of the logic analyzer itself is more complicated. We have data acquisition as a unit, we have a channel count and memory depth, and we have analysis and display. One more thing, for the oscilloscope it applies to digital and analog. It applies for both, but it is more focused on analog, although it can be possible for digital signals. However, the logic analyzer is mainly used for digital signals and analyzing digital signals. It can be also applied for analog signals, but it is more practical for digital signals. Okay, and this is its composition. You don't have to memorize this, you just need to have an idea, that's it. We have probes. The probes allow you to connect between one part of your own design to a testing device. You can see these are connectors here, the small ones. You can connect them, attach them to some part for testing purpose. Maybe you need to see if they work properly or not. And we have two types. One of them we call multi-channel. Multi-channel, that means like this. Look, we have many channels. Or it could be one single channel clip on probe. This is single channel here, but this is multi. If you have a probe that has only like this single channel, in that case it's called single channel clip on probe. It depends on the application that you are in need of. If you need multiple channels or multi-channel, then you can use this kind of probe. Now, do we have it in multi-sim? Yes, and we will be using it for some applications later on. A signal generator, of course we need to have a signal generator. Why? Any design, in order for you to check if it is working or not, you need to feed it with an input. Where do we get this input from? We need signal generator. We need to have an input source. So the input source could be a logic signal source, ones and zeros, series of ones and zeros, depending on what kind of stream you want. It could be a counter, it could be of anything. So we have a logic signal source. That's series of ones and zeros. Or it could be arbitrary random, actually, waveform generator. We have different types of waveforms and functions. They could be triangle, sine waves, or they could be also pulses. So we have different types, and also you can feed a mathematical equation to create a waveform for you. That's why they call it arbitrary. So this is the arbitrary one. This is the function generator, the one that produces mainly logic functions for you, although it provides other types of input functions, but this is the most common type, the logic functions that we may need to use. Maybe you are familiar with the digital multimeter. The digital multimeter allows you to measure AC and DC voltage, current, and also resistance. We also use it for testing diodes if they work, capacitors, and if we have a short or open circuit. These are actually very practical, and most people who are technicians or work in the field of electricity, or they are electricians, they need them. Something like this. This is a cheaper one. This is the complicated one. We call it bench type. This is the handheld type. It allows us to measure either alternative voltage or DC voltage or the resistance. Maybe here we measure a diode, if it is spoiled or not, and so on. You can convert also between different things and measure based on your own application. This is usually we have those in laboratory, something like this, the bench type. It's not handheld, you don't carry it in your hand, by your hand, but it helps you to measure if there is any short circuit, if a component is working properly or not. Okay. The last part is the DC power supply. Why DC? All digital electronic require a power supply which is DC, and this kind of range usually work between 1.2 to 5 volt DC. So where do we get the DC power from? This one gets supplied from the wall, from the standard electricity we have, which is alternative, and it converts it to a DC supply, and then we can control the level. Let's say 5 volt, we want DC, we can use it, and that will allow us to get the power supply of our need. And this is the end of chapter 1. I'll try to create the videos of next chapter very soon. Until then, have a good time. Goodbye.